I'm going to discuss, I'm going to leave you with for you to solve on your own the case of both constant electric and magnetic fields. You just have to put these two cases together, right? And if you find it difficult, we'll do it in the next class. Otherwise, it would be nice that you do it on your own. And again, then take the limit of B being much, much smaller than C and see the result that you had in your electricity class, right? Okay, so first case that we are going to discuss today is the case of constant electric field, right? Since we always have a choice how to choose our coordinate system, how to place our coordinate system. So whatever be the direction of the electric field, let's say I align my coordinate system in such a way that my electric field is along the x direction. So, and the magnitude is E, right? So my electric field vector is then E x cap, right? It's along the x direction. I have chosen my coordinate system in such a way. Right now, if I choose my electric field to be along one of the directions, then we know how does electric field act on charged particle. The motion of the charged particle will be restricted to a plane, right? Now again, I can always choose that motion to be, let's say, only in xy plane, right? As we will go and do the mathematics, as we proceed with the mathematics, you will realize that there is nothing particular, there is nothing in particular, there is nothing that I have in choosing the motion to be in xy plane, first thing. Second thing, I can actually choose the motion not to be restricted only to xy plane, but in general in 3 dimensions, that is along x, y, and z, and my answer will not change, right? So it's not a big deal that I choose that motion to be along or motion to be restricted in xy plane, right? But for simplicity, let's say that I choose my electric field to be, I could have chosen XZ plane also. It's not a problem, right? And not include Y in my calculation at all, right? So with this, I can now to remind you what we had from our previous class is the equation of motion for a charged particle in electromagnetic field, right? Now, since I have only electric field, my Lorentz force or my equation of motion reduces to dp by dt equal to E times E, right? Which will give me, if I take the x component of this equation, this vector equation, it gives me px dot equal to E times E, because it will give me E times Ex, and Ex is E, and it will give me Py dot equal to 0, because I have chosen my electric field to be along the x direction, right? Now, I can integrate these two equations. When I integrate my first equation with respect to time, I get Px equal to E times t plus some constant. I can always choose my constant in such a way that at time t equal to 0, my body is at rest, my particle is at rest. So my Px at time t equal to 0 is, let's say, 0. So my Px at any time t is then E times t. This equation will give me Py is a constant. Let's call that constant as some P naught. Now, what is the aim? What are we interested in? What am I going to do with all these equations? My interest is to solve this equation. Now, this is equation of motion. The idea every time is to solve the equation of motion and get the trajectory of the particle. So that's what we are heading towards, is that I want to solve these equations, write them in terms of quantities that I know or I can measure, and arrive at the trajectory, that is, solve these equations for x, y, and z as a function of time. That's what we are interested in, right? So now what do we have? I'll have to erase this, and what do I have is then px as a function of time equal to EET, and Py is some constant P naught. Right? Now I can write the kinetic energy of my particle using the relativistic equations like this. What is P square? P square is Px square plus Py square plus Pz square. So this equation or this expression for kinetic energy becomes m square C4 m square C4 plus P naught square C square plus EET C whole square to the power half. I have substituted for Px and Py. Right? Now at time t equal to 0, this is my initial kinetic energy. It is some constant. So let's call it E naught. And then I can write this expression for my kinetic energy as a function of time. Like this. Right? Now, what is the use of doing this? The use of doing this is, I will remind you, if you go back and look at these quantities, Px and Py, Px and Py here are relativistic momentas. This is not simply equal to mvx or mvy, right? You should always keep that in mind. That is something which is very, very important to remember. Otherwise, I would have just integrated here and obtained a solution to my differential equation. But you have to remember that these are not simply mvx and mvy, right? That's why I have to do all this, right? Why? Because to get x and t, what do I need? I need dx by dt. That's what we always do even in Newtonian physics, is that I do dx by dt, I get dx by dt, I get dy by dt from my equation of motion, integrate them to get x and t as functions of time. I cannot do that here. That's what I'm trying to tell you. It is important to remember that I cannot do it here because this is not equal to mvx and this is not equal to mvy. They are relativistic expressions. You have velocity, magnitude sitting in the denominator also. You have, these are actually gamma mvx and gamma mvy, right? That you always have to remember. But if I know kinetic energy and if I know momentum, there is a way to write velocity, right? We discussed this when we were discussing initially relativistic mechanics. Is this expression, right? Because I want to write V is that I wanted kinetic energy. And that's why I had to write this expression here, right? This is, now I can use, now I have my vector momentum, the relativistic momentum. I have my relativistic kinetic energy. You can see that this is going to reduce to m into v only when kinetic energy is when you go to the limit of Newtonian physics and you replace kinetic energy as in terms of the Newtonian expression for your relativistic kinetic energy. Then you get back your expression for P is equal to mv. Otherwise, V and P are related in relativistic kinematics like this, right? So that is why to write my V, I needed both P and E kinetic, and I have them now. So now I can write from here. Now from here I can write my Vx, which is dx by dt as px c square by E kinetic energy, right? And now I substitute for px, which is E et, and c square is already there, and expression for my kinetic energy, which is some E naught at time t equal to 0 plus c e t square to the power half. Right? Now it is not difficult. I have dx by dt. I can integrate. When I integrate, I get, you can see that you just need to square this because you have something similar. So I divide and multiply by E and E. C is already squared. And if I do that, I'm going to get this, right? Now again, I can fix this constant using my initial conditions. I can choose my initial condition always to be such that at time t equal to 0, my particle, charge particle, starts at the origin. So this gives me A equal to 0. And I have my xt as simply okay. Let me call this as equation number 1. Now, Vy dy by dt will be Py c square E kinetic energy. Py is a constant, P naught, c square. Even kinetic energy is a constant. Not a constant, sorry, it depends upon time, but I know what kind of time dependence it has. I can integrate this. If I integrate this, this is a sine hyperbolic function. And what I get after integrating, one of the c is going to get cancelled with the c in the denominator. And what I'm going to get, sine hyperbolic inverse of c t by E naught. You can do the integration. You can redefine your variable t and see that this can be written in the form of 1 plus, so you can reduce that to hyperbolic function, and then you integrate and you get this. So let's call this as, again, I would get an integration constant b, which I can fix using my initial condition that at time t equal to 0, so I get b equal to 0. So I have my expression for y and x. Let's call this as equation number 2. Motion in all the 3 coordinates. That is, I look at motion in 3 dimension, and I here, right? It's not going to matter at all. You will realize when I am just going to do the substitution, it is just going to add to a constant in my equation, right? So for the time being, I go back to my assumption that, let's say, or I go back and I work under the same conditions that, let's say, my motion is only in xy plane, right? So then I can find the equation of my curve. I can eliminate t using my second equation and substitute it into my first equation. If I do that, I simply get my equation to be something of the kind and I substitute for t from here into my equation for x here. In fact, I can actually substitute for CET from this equation, right? And if I do that, I get the equation for my x as so this gives the equation. These are the two parametric equations, xt and yt, and this gives me the equation for the curve in xy plane that my particle is going to follow. Now, is this correct? Now, this is an expression that I have got in relativistic mechanics, right? There's a way to check whether what I have done is correct or not. What is that way to check? Is that I look at this equation in the limit for v being much, much smaller than c. If v becomes much, much smaller than c, then this is my Newtonian limit. My P naught, which was relativistic momentum, reduces to simply mv naught. That is my expression for Newtonian, and I'll be Newtonian momentum, and my E naught, we've seen that, will simply reduce to mc square, right? The kinetic energy. So the rest energy, which we normally do not include otherwise in Newtonian physics, but we have seen that when I take the classical limit of my relativistic expression, energy agrees with expression for Newtonian energy except for this term. Why? Because when we do Newtonian physics, we never talk about the binding energy or the rest energy of the particle in itself, right? But we have to take care of this expression here because we have seen what the limit of energy is when I go from relativistic mechanics to Newtonian physics, right? And if I do this, I can see that here in this expression, I can now expand. So if P naught is my relativistic expression, and I can do the expansion of sine hyperbolic term here. And what the expansion will be, the expansion for sine hyperbolic expression here will simply be just if you take the limits. In fact, I can simplify this expression further. It even makes it simpler to look at, is that I can write this expression as E naught cos of hyperbola yt e by p naught c. Because this is 1 plus 1, if I take E naught common, this is 1 plus sine hyperbolic square. So this is actually this. Now the expansion is even simpler, is that what is the expansion for cos hyperbola? The cos hyperbola expansion will simply be equal to 1 plus half square of this term. Xt. So this is some constant. I can always ignore this constant for the time being, but what is important to see is the variation, is the relation between x and y. And what kind of curve does this look? This is a parabola. And we know, you go back, see your electricity, magnetism, look at Griffiths, you will see that when you have a charged particle moving in a constant electric field, then the motion of the charged particle in xy plane, that is the plane containing the electric field, is actually a parabola. Right? The motion of the charged particle in the plane containing the electric field is actually a parabola. Right? So you see the expression that I get here, this expression right here, for the relationship between x and t in relativistic mechanics is hence correct. Right? Okay. I'll wait for 2 minutes if somebody wants to ask anything. And in the meantime, I'll take a picture of who all are there.
Ma'am,
Yes.
here we are using the assumption that the motion is in the xy plane only. But in between, you also showed that if we take it in general, let's say if we take it in 3 dimensions, then we do get an expression for z of t, which is same as y of t. So
What
how
will
are
you
the
do
two
then?
things?
How will you combine x, y, and z in that case? Is that you will that you can combine your motion in yz, the yz motion, into one particular, you can call it, let's say, longitudinal motion, or let's say transverse, whatever kind of, sorry, the transverse motion, not longitudinal motion. You can combine into something of the kind which you can call, let's say, y square plus z square with some magnitude, and you will be able to again reduce your expression to an expression for a parabola. I leave it to you to figure it out. You can actually do it. It's not difficult to see. You'll be able to redefine your variables in such a way, combining y and z, so that you again see that that the motion is like x and that new parameter here, it will be parabolic motion, right? So that motion along, even if you just think about it, even if you just do not do any mathematics and think about it, you realize that that motion is not really going to affect your motion along. What really is going to affect is the way the electric field, moment you see a parabola, moment you see a parabolic equation, you realize that your motion has to be restricted in a plane. And you can always realign your coordinate system in such a way that that plane in which the motion of your charged particle is restricted should be a plane containing your electric field. First thing, very important. And you can always redefine that plane to be either an XY plane or XZ plane, depending upon it. Suppose I choose my direction of electric field to be along X, I can choose it to be XY plane or XZ plane, right? I don't need to do the problem in 3 dimension at all. You must understand that choice of your coordinate system should never, even if you don't look at that assumption in the beginning, you solve it with this and you get in the end that you see that motion is a parabola, right? Now you must understand parabola is something that can always be contained in 2 dimensions. It can always be contained in a plane, right? So it tells you that whatever be your choice of coordinate system to begin with, you will always be able to choose a set of generalized coordinates, make a change in such a way that you get an equation in this form. That's the whole idea of generalized coordinates, right? What we talked about in the beginning, right? So I leave it to you. You should actually include that Z expression. It is not difficult to get that Z expression. That Z expression will be exactly same as my expression for, even if you do not choose initially, as you can actually start with the most general problem, is that you can have an electric field along any direction. Do not restrict it along X direction. And you can write down expression for Px, Py, Pz. All 3 of them containing Ex, Ey, Ez. Right? You will see that ultimately your equations will show you that there is a possible choice of generalized coordinates that you can always make in such a way that your equation can be reduced to equation in a plane, right? And that equation in a plane will always be a parabola. You should do that.
Okay,
let's add that as a task. I'll add that as a task to our tutorial, next tutorial sheet. Is that to start with the most general problem. Choose Ex, Ey, and Ez and make a choice of generalized coordinates.
Okay, thank you, ma'am. I got it.
So what I'll do is I'll have to end this meeting and restart. To begin with, there were 23 people. Now there are only 21. I'm going to take a picture once more in the next 40 minutes, right? In the remaining class after I restart.